Sometimes I get my grade 12 students to come into my grade 10 classes because it's one thing if you're like, if your teacher says it's important, it kind of gets old because you feel like, oh, the teachers say everything is important. So it's sort of like, oh, another thing the teacher said is important, and you just sort of brush it off. But this is a topic that I sometimes bring in my grade 12, so you can actually, and if you have older siblings that are taking pre-calculus, like ask them, how important is it that you are good at factoring? And they will say, it is so important. It comes back over and over and over again. So if we can learn it really well the first time, it's going to help you over and over and over again. And if we find it difficult and don't put any work in the first time, it's going to be difficult over and over and over again. So it is something that is really, really important for equation solving and for mathematics leading forward. It's the undoing of multiplying. It's like the dividing of algebra. So you know what multiplying is? You've multiplied things before. But if you had 4 x's, so what does it, and these are called algetiles. Have you seen algetiles before in grade 9? So the idea with an algetile is the x algetile, if you put 1's right beside it, you're like, how big is the x? You actually don't know, because it doesn't work out nicely. Or it's supposed to be, and is designed to be, right? Oh, not perfect. So you don't get the misconception that, oh, this x is equal to 7, or this x is equal to 6. We don't know what that x is. That x could be anything. And the idea is if we had, I need 2 more of these, 4x's plus 8, could we actually take them, rearrange them, and make a rectangle? Well, obviously you can't put the 1's on this side, but I want you to notice that a 1 matches up perfectly on this side. And that's the reason, is that each of these algetiles represents an area. So we have one side we don't know, which is x, and the other side is 1. And if I did length times width, x times 1, that area would be x. And a 1 tile has an area of 1 because it's 1 by 1. So 1 times 1 has an area of 1. And what I showed you a little bit yesterday is that anytime you multiply 2 things, you can represent it as a rectangle and area. So what we want to see is, can we rearrange these x tiles? And the only places I can put x's is touching another side that's x. So I'll have to put all 4 of these together. And the only places I can put the 1's would be touching a side that has 1. So I'll put 4 of them there. And 4 of them there. And that makes a perfect rectangle. What are the side lengths of this rectangle? Well, if the x tile is x by 1, can you see that this length right here, oh, that's not very easy to see. I'll just get rid of the, from here to here, does it make sense that that's 4? Because each of those sides are 1. So if I had 4 of them in a row, just like the 4 1's in a row, that would be 4. And this side here is an x plus 2 more. Algetiles are really nice at the beginning for seeing what happens. They are extremely annoying for actually factoring, because who wants to draw out, what do we draw, 12 little things and put them together? It's kind of annoying, but it does help us understand it. So the idea here is that if I write 4x plus 8 as a rectangle, I can say that the answer, because that's the area, is equal to 4 times x plus 2, because that's the length and the width of that rectangle. Can you see that this might be really annoying if I gave you something like 55x, 55x's plus, I don't know, 11. You'd have to make 55 of these and take 11 ones and try to put it somehow together to make a rectangle. Now, the idea is, when we look at the 4 and the 8, do you see that there's one number that divides both of those? Well, there's more than one number that divides those, but it divides both by 2. But the biggest number that divides both of them is 4. And if I take a 4 out of the 4x, I just get left with an x. And if I take a 4 out of the 8, I get left with the 2. And one way that we show, right, do you remember distributing last year in grade 9? So if you had that answer of 4 times x plus 2, that 4 would multiply by the x to give you the 4x. And the 4 would multiply by the 2 to give you the plus 8. What's the biggest number that can divide both 55 and 11? Can you see that it would be 11? And then if I put the brackets here, and this had to multiply to give me 55x, can you see that there would be a 5x left? That would give me 55x. And if I have a plus sign, I'll need a plus sign here. And 11 times what is 11? 1. So if we drew out 5x's on one side plus 1, and 11 on the other side, and filled it full, it would make a perfect rectangle. But that wouldn't be very much fun because it would be a lot of drawing. We are going to start by doing some of these drawings with algebra. Right? What did we do? We made our rectangle into the most compact rectangle that we could. We also try to make it as close to a square as possible, and then find the lengths and the widths. X squared are tiles that have an x on one side and x on the other side. So if I had 2 of those x squared, they would look like this. I'm going to put them this way. And then we need 6 x's. 1, 2, 3, 4. So I can only attach an x side to an x side. I can rotate these x's, but this case looks like I don't have to. There we go, I made a perfect rectangle. These sides, of course, are 1, 1, 1. This is x, this is x, this is x. So can you see that this whole side is 2x, and this whole side is x plus 3. So that means that 2x squared plus 6x is equal to 2x times x plus 3. One of the beautiful things about factoring is after you've factored, you can distribute to actually check, does it work? And 2x times x is 2x squared. And 2x times 3 is 6x. But if we were doing a similar one without algebra tiles, right? Let's say I had 8x squared plus 20x. First, I would look at the numbers. The 8 and the 20, what is the biggest number that can divide both of them? And again, your times table comes into effect. Very important. The biggest number you can divide both of them is a 4. Then you look at your variables. Question? Then you look at your variables and say, is there a variable in common in both of them? And they both have an x. So I could also pull out an x. Then I look at what's left. If you pull a 4x out of 8x squared, well, to make the 8, you would need a 2. And to make the x squared, x times x is x squared. And if I pull a 4 and an x out of here, well, there would be no x left, but 4 out of 20 would leave me with 5. Again, you can do a quick check to see if you're right. And that should be a habit with factoring. You should do a quick check to see if you're right. Okay? What happens if you only see the 2? Okay, because this could sometimes happen. A person says, I can divide both of these by 2, so they pull out a 2x, and then they get 4x plus 10 left. That's not wrong, but it's not factored completely. Sort of like simplified form, you have to factor something completely. There is still something in common in the inside. What's in common with the 4 and the 10? You could still pull out another 2, leaving you with 2x plus 5, and then this 2 and this 2x is the same as 4x, but we do want to see that greatest common factor first if we can. So factoring without delta types. You look at all the terms and you see if they have anything in common. So first you look at your numbers. Is there something that divides both 2 and 4? Yes. What's the biggest number that divides both 2 and 4? 2. So you pull out a 2. Then you look at your variables. Is there the same variable in each term? There's an x here and there's an x there. How many x's are in the first one? There's x times x times x. There would be 3 of them multiplied together. And this x squared means x times x. That would be 2 of them multiplied together. You could pull out 2 of them, leaving you with, well, I pulled out the 2. I pulled out 2 x's. Can you see that in that first one, you only need 1 more x to make 2x cubed. And in the second one, you could pull out an x plus 2. So we're looking for that greatest common factor. One thing you can do to check if you had the greatest common factor is after you factor, check what's left and say, is there anything in common with the x and the 2? There's not. So if there's nothing in common, you know that you factored it completely. If there is something in common, you have to keep going. It just means that you didn't pick the biggest one to begin with. Sometimes people are like, oh, I should have picked a bigger one, and they just sort of scribble it out and start over again. That works out fine as well. And like I said, once you're done, you should always distribute or expand to see if you get the original question. If you have 3 terms, it's still the same idea, but now you're looking for something in common in all 3 of them. And if you have negatives, you have a choice. So I'm going to do this one in 2 different ways. Method 1, I'm going to pull out a 3, because that's the number that divides 3, 3, and 6. And then I look at my variables, they all have y's, but I can only pull out 1 y, because the last one only has 1 y. That would leave me with negative y squared plus a y minus a 2. Lots of mental math. I check it. 3y times negative y squared, negative 3y cubed. 3y times a plus y, that gives me 3y squared, and 3y times negative 2, negative 6y. I look at my terms that are left, and there's nothing in common with those three terms when we're done. Okay? So some terminology that I'm using here. When things are connected with adding and subtracting, we call each item a term. So this is something with three terms. Do you remember from grade 9 what we call an algebra thing with three terms? What do you call something that you ride with three wheels? Tricycle, right? You've seen that word tri before because it has three things? Tricycle, this is a trinomial. It has triangle. If it has two terms, just like a bicycle, it's a binomial. Multi, all of these are called polynomials. Poly means more than one. Okay? You could have also, and I'll do it in purple here, taken out a negative 3y. So you have a choice with the negative. Do you pull the negative out, or do you leave it in? If I pull the negative out, this one would be positive. This one now is negative. And this one is positive. So it's a bit of a choice. Me personally, I like pulling out the negative. So I want you to try a couple on your own. We've got A, B, C, D, E, and F here. First one, the biggest number that you can take out of all three is a 2. Then looking for letters that they have in common. They all have a B, and they all have a C. What am I left with here? To make the 6, I would need 3. And I've got to be in the C, but I still need an A. It's going to be a plus sign. And then 2 times 4 makes 8. I've got to be in the C, but I'm missing the D. And then the last one's a minus sign. I don't need any numbers because I have the 2. I don't need any, what do I do if I pulled out everything? 1. I'm left with a 1. And then again, quickly multiply it out in your head and do a check to see that you're right. Yay. Okay, second one. 18 and 12. Biggest number you can pull out is a 6. There are no variables in common because the second one doesn't have any variables. So then, for my first one, I would need the 3 to make the 18, and I still need the p cubed. And I pull out a 6 out of the second one is a 2. Do a quick check. How did you do? Pretty good? Awesome. Did you not see there was more on the next page? Oh, I have to give you a little bit of, okay. I'll give you a little bit of time. Third one. 2, 4, and 8. Did you see that you could pull out a 2? And then looking at the variables, there is an x in common, leaving you with still 2 more x's in that one, a 2 and an x in this one, and just a 4 in the last one. Do a quick check by multiplying it out to see if it works. How did you do? Good? So again, first we look at the numbers. So what could make the numbers harder? Just if the numbers got bigger, right? If the numbers got very big, it would be harder to figure out what common factor you pull up. Most of the time in high school, the numbers don't get very big. So I can pull out a 3. When I look at the variables, they both have an m, they both have an n. This would leave you just with 1 and 2, and there's still an m and still an n left. Does it matter the order you write your variables? No. Generally, they do it alphabetically. Okay? Has anybody else ever had trouble figuring out which one comes first, M or N? Because they look so like kind of similar. Top of it. I always remember the M comes first because it's bigger. It's like I'm going first, just like a little bit of a bully. But I don't know if that's true.
Were you a bully in high school?
No. I was not.
Sure. Seems kind of like the bully type. Wow. Just to make fun of people.
I just like to make fun of you. Okay, with the numbers, there is a 3 that you can pull out of all of them. And then looking at, they each have one S, they each have one T, leaving you with 5 minus 7, one S, one T left, plus 2, and 2 S's left. So when you factor something out, it's like you're taking it out, it's like you're dividing it out, and you're finding out what is left. How did you do? How many do we have left? One more? One more. Whew. Again, if you look at the numbers first, what divides 6, 12, and 30? 6. So your times table comes into play because you need to know quickly what's the biggest number that divides any. Next, we look at the variables. I think the variables is actually easier. Is there an x in all 3? Yes. How many x's can you take out of each? The most you can take out is 1. What about y's? Yes. And 1. So then what are we left with in the first one? You took out the 6, you would still have x squared, and you'd still have 1 left. Minus. Take out a 6, you get a 2 left. And that's it, because the x and the y were pulled out. Plus, take out the 6, you get a 5. Took out 1x would be left. Took out 1y, you would have 4 y's left. Multiply it out and check. This is called factoring. Okay? So going in this direction, from here to here, this is the instruction you would get. Okay, so it's important to know not only what to do, but it's also important to know what the instruction word would be on a quiz. Because if you don't know, when they say factor, you're like, what did that mean? Well, then it doesn't matter if you know how to do the math, you won't be able to do the question. Okay? This way, you'll get the following words going backwards. Either expand or simplify. That means get rid of the brackets. Mathematicians generally don't want brackets in some cases. So they say, can you expand and can you simplify? We are going to find out that one of the most complicated commands in a math question is the command to simplify. I can think of at least 20 to 30 different things that it means. That makes it complicated. And then yet the word says simplify. So, right? Because you've used simplify before, right? You've used simplify with fractions. If I have 3 over 6 and I say simplify, what are you supposed to do? Put it in lowest terms, right? Change it to 1/2. In polynomials in grade 9, you had simplify. If you had 2x plus 5x and it said simplify, you're supposed to know to combine like terms. Simplify also means get rid of brackets. Simplify also means add, subtract, multiply, divide if you can. It means a lot of things. And so every time we learn a new topic, we add something to what does simplify mean in this situation. Okay? So, next thing we're going to do is we're going to multiply. You could also write above this one. You could get this command word, means the same thing, to expand or to simplify. And you could do this with algebra tiles, although we will not very often do it with algebra tiles. Multiplying is always an area. So you could have a length and have a width and have 3x plus 2 and x plus 1 and see what you get. We're going to learn a couple methods. One of the methods is called FOIL. And FOIL is just fancy distribution. Okay? So when you expand and distribute, normally you'd have arrows going to this one. You would also have an arrow going to this one. This one would go to this one, and this one would go to this one. And FOIL is just an acronym that when you multiply your first ones, that's that first arrow. Then the O says you've multiplied the outside ones. That's right there. The outside one being the 3x on the one outside and the 1 on the other outside. If O is outside, any guesses what I stands for? Inside one. That's right here. I multiplied the inside ones. And any guess what the L stands for? The last one. So it's just a way of remembering to distribute. And FOIL has 4 letters, so you know you have 4 arrows that you have to do. And you'll often hear in an English class, oh, you just need to FOIL that one. That's not an actual math word, or, well, I guess maybe it's been used enough, it's actually a word enough. But it's not something that if you talk to someone in French class, they'd be like, I don't know what that means. So it's just a way to remember. So now, if we FOIL this one, what we would get is 3x times x. So maybe I'll rewrite it, 3x plus 2 times x plus 1 equals. And if you multiply the first ones, the 3x times x, you would get a 3x squared. And I'm going to put an F just over top of that to say that was our first one. When I multiply the outside ones, I would have 3x times 1. That would be plus 3x. That's my outside one. The inside one would be 2 times x, so that's plus 2x. My inside one. And finally, 2 times 1 is plus 2. That's my last one. And we have to simplify if we can. Do you see that there are like terms? Remember from grade 9, like terms just means that they have to have the same variable and same exponents, not the same number in front. So the 3x and the 2x, I'll underline them here in purple, those are like terms. And generally, when we multiply out 2 binomials, you will notice that the first ones always show up there, the last ones show up there, and the outside and the inside will often be like terms and get combined. This is going to cause us some problems later on, because we're going to find out that it's really easy to FOIL, because you just have to follow steps and combine like terms. It's not going to be as easy to factor, because you're going to get the answer and be expected to come up with the 2 things that multiply. But we'll get to that, and that is, I think, a fun challenge. You could do the chart method. I actually quite like the chart method as well. Chart method looks like this. It is very similar. The chart method idea is very similar to the area method for multiplication I showed you yesterday. Remember when I said, hey, let's multiply 17 times 16? Well, you don't know your 16 times table, so instead we went 10 plus 7 and 10 plus 6, and said this area is 100, this area is 70, this area is 60, this area is 42, and add them all up, and we get 272. The chart method does the same thing. You make a box with an area. And for our question, which was 3x plus 2 and x plus 1, you make an x and a 3x, and a 2 and a 1. And it doesn't have to be to scale, because technically this 3x should be 3 times longer than that x. Does that make sense? If I drew it perfectly to scale. But if I do this, 3x times x, that will be 3x squared. X times 2, that will be 2x. 3x times 1, that will be 3x, and 1 times 2, that will be 2. And if you add them all up, 3x squared, I notice these two are like terms. So I can just go plus 5x plus 2. Okay. Initially, comparing FOIL and the chart method, I think the chart method is easier to see and understand. The negative of the chart method is it takes more space. So over time, teachers and students stop using the chart method just because they don't want to take up so much space in their notes or in their homework. Eventually, right now my grade 12 students, if they see this, they go and write the answer right away. They're like, oh, the first one's easy, 3x squared. The last one's easy, 2. If I do my outside and inside, I can do that at the same time and add them and get 5x right away. Generally in grade 10, we take the extra step, write out all of FOIL, and then add them. But by grade 12, they'll just do that all in their head and get the answer right away. And the least favorite way is algebra tiles. So the algebra tiles way, we had 3x and the other one was 3x plus 2 and x plus 1. So, okay. So you take your 3x plus 2 and you line that up. It's very similar to the chart method. You take your 3x plus 2 and line that up on one side. And you take your x, which we'll have to rotate, plus 1, and line that up on the other side. And that makes a big rectangle. And we have to fill that rectangle up. So when I have x times x, that's going to fill up with an x squared. And another x times x, that's going to fill up with another x squared. And another x times x will fill up with another x squared. X times 1 will fill up with an x. X times 1 again will fill up with another x. And x times 1 again will fill up with another x. X times 1 this way will fill up with an x. And finally, the 1 times 1 fill up with 2 little squares. And we fill in the whole rectangle. So for drawing purposes, the algebra tiles is not very much fun. We have actual algae tiles anytime you want. You can grab some and play around with them. Playing around with them is a little bit more fun, but you'd still find that it probably takes you longer to do that than the other two methods. Now that you've got the box, here's the rectangle, outline it in blue. Now that you've got that, you say, well, what's in that rectangle? I have 3x squared, I have 5x's, and I have 2 1s. So I get 3x squared plus 5x plus 2. So I hope you understand the algae tiles method, because sometimes on quizzes there'll be questions, multiple choice or short answer, that'll say, can we show it with algae tiles? But generally, we're going to use our chart method and FOIL more often. Okay, again, I really like the chart method because if you haven't seen this for multiplying numbers before, it's really powerful for doing mental math, and that idea is the same there. Algae tiles gets a little messy, especially when you get into negatives. Do you know that if you want to show an X tile that's positive, you would draw it and shade it in? And if you want to show an X tile that's negative, you draw it and don't shade it in. So filled in tiles are positive, not filled in tiles are negative. But we're not going to do this. First, outside, inside, last. It's going to equal my first ones, minus 2x squared. I'll put an F around that. My outside ones, plus 1x. And you can write plus 1x if you want, or you can just write plus x. Everybody okay that if there's nothing written in front of the number, that there would be a 1? Okay? And then my inside ones, negative times a negative is positive. And my last one's a negative 1 times a positive 1 will be negative 1. Combine my like terms. X plus 2x gives me 3x's minus 1. So my first ones are here, my last one's here, my outside and inside got combined again. This pattern is going to be super important once we start to factor. Because we're going to have to try to break this up into an original one. And I want to do that so bad right now, but we have to practice multiplying first. We did the last one with FOIL. I'll do this one with the chart method. So using the chart method, you'd have 2x plus 7, 3x and minus 5. And this is really not to scale, right? You can, if you like to draw it a little bit more to scale, you can. But it's kind of hard to draw minus 5 to scale. Now we just fill in the boxes. What's 3x times 2x? That's 6x squared. What's 3x times 7? 21x. What's 2x times minus 5? Negative 10x. And minus 5 times 7? Negative 35. So it equals 6x squared. 21 minus 10 will be plus 11x minus 35. And with FOIL, this would have been your first ones. This is your last ones. Check. Do your first ones make that? Do your last ones make that? And your outside and inside got combined to give you 11. All right, so I've showed you. Oh, did I skip one? Yeah. Okay, the one I skipped, and then there's 2 more. Well, there's actually 5 more. I'd like you to do 2 with FOIL and 2 with the chart method. Doesn't matter which ones. I'll put up the answers in a bit. So we've got 5 left to do.